Hello all. In this video, we will cover linear and exponential models from section 8a. Recall from the last section that the linear model can be expressed as y equals mx plus b, m being the slope or the rate of change, b is the y-intercept. For these specific problems we're going to model with lines, the x value always represent our input. And in these problems, it's usually time. And the y value is going to represent our output, or some future value. The role of the y-intercept is a little different in the linear model, because x is being represented as time. So along the x-axis, when you cross the y-intercept located along this axis, we can refer to this intercept here, the y-intercept, as our starting point. Examples of linear growth can be found all over. But suppose I have something that starts as a sequence, maybe 5, and then 10, and then 15, 20, 25, and so on. We can see that our rate of change is constant. That rate of change, whatever it is going to be played by the role of m. In this problem, we can see that the rate of change is a constant addition of 5. And for linear problems, the rate of change is always going to be an addition or subtraction of the same number over and over again. But what happens if the rate of change is not the same number over and over again? Or what if a different operation is being done instead of addition and subtraction? Well, this is where we get to exponential growth. So, another example. Suppose I start with 5 again and 10, but now instead of adding a number over and over again, I'm going to multiply a number over and over again. 40 and 80 and 160 and so on and so forth. Now the rate of change, even though it looks like it's the same, it is not. Because as I add from one value to the next, this is only an increase of 5, and then 10, and then 20, and then 40, and so on and so forth. So we would refer to this as a variable rate of change. Which is exponential. But we have a way of modeling the line. So it would make sense for us to find a way to model this kind of rate of change. It turns out we come up with a new equation. The exponential model looks like this. Q is equal to Q naught times 1 plus R raised to power T. Q naught here is going to be the initial value, kind of like the y-intercept in the linear case. The R value is our rate of growth or decay, and it's a percentage that we express as a decimal. T naturally is time. That is our input. And this Q by itself on the other side is our future value or our output. And now that we have everything labeled out for the exponential model and the linear model, we can begin to do these examples that we have over here on the left. So let's start by putting these numbers up here at the top, or these formulas on the top. Y equals mx plus b. This is our linear case. The new one we're coming up with today. Q is equal to Q naught times 1 plus r to power t. This is the exponential. So we're going to look at a couple of these examples here, and our goal is going to be the following three things. One, we want to determine is it linear or exponential. Two, we want to build the equation. And then lastly, we want to find a future value. All three of these are fair game on the exam, and they're usually really closely tied together. So most likely I would give you a problem on the exam and ask you all three of these questions. I'd give you some sort of a situation. I would ask, is this a linear model or an exponential model that would best fit this? Then I'd want you to show me what does that model look like. And then lastly, find a future value, or tell me what the value's going to be in 5 years or in 6 hours or in some period of time later on in the future. So we'll go through these 4 examples right here one at a time. Hopefully we'll get a little more understanding of when we use linear and when we use exponential. What I will say as some key words to telling us that we're using linear or exponential, when we see a percent change, we are immediately thinking exponential models. Remember, exponential has that value r. R is a rate. We can express it as a decimal. Also, anytime that you see something that's increasing by a constant amount, this should be indicators of linear. So we'll go with number 1. It says the price of gasoline has been increasing by 10 cents per year. If it's $2.50 now, what will the price of gas be in 5 years? So, again, the important keywords here, increasing by 10 cents per year means that the rate of change is constant. It keeps growing 10 cents and 10 cents more, and so on and so forth. And so we should expect this to be a linear model. So we know we're going to be using that y equals mx plus b. What information can we plug in there to build the model? Well, we know that the rate of change, m, is 10 cents per year. Notice that everything else is in dollars, $2.50. So I'm going to express this in terms of dollars also as 0.10. The b value, or the starting out point, is going to be what the price is right now, current value. Turns out it's, according to this, $2.50. With those two pieces of information, we can build the linear model. Y equals 0.10x plus 250. It's also very important for you to keep in mind what unit x is being measured in. So it's telling us here that the increase happens per year. So our time we should be thinking about in terms of years also. Just to verify, it does tell us what will the price of gas be in 5 years. And so in this case, our x value is going to be 5. It is important, though, to keep those units the same. This unit right here and this unit right here are the same. I could give you an example. It says here that gas is increasing by 10 cents per year. I could have said if it's $2.50 now, what will the price of gas be in 6 months? And now, because everything is being measured in years, 6 months is only a half of a year. And so x would actually be 1.5, not just 6. So it's important that these two units are lined up. So we're going to plug in x equals 5 in order to find our future value. We have y is equal to 0.10 times 5 plus 250. That's 50 cents. A 50-cent increase plus the 250 that it already was is going to tell us that in 5 years we can expect gas to be $3. Try another one. Number 2 says, put these formulas back up here too. Number 2 says the price of gasoline has been increasing by 5% per year. So as soon as we see that percent change, we should be thinking exponential. We can build the equation. Remember, we start with Q is equal to Q naught times 1 plus R to power T. And here it said it's increasing by 5% per year. So our R is 5%. We always express R as a decimal in our calculations. In this case, 0.05. The Q naught is that initial value, which is $2.50. So our model, based on these two pieces of information, should be Q is equal to 2.50 times 1 plus 0.05 raised to power T. I'm going to combine like terms in the middle here, and I'll write this out and in its correct form as 2.50 times 1.05 raised to power T. There's our model. It asks what will the price of gas be in 5 years. So now the role of little t is 5. We can plug that in using our calculator. We're going to get Q is equal to 2.50 times 1.05 raised to the 5th power. So in our calculator, we'll go 2.50 parentheses 1.05 close, and we'll raise it to the 5th power. And we should round to the nearest cent. And so we'll say in this one, gas price we should expect to be $3.19. We'll try another. Example 3 says the price of gas has been falling by 5 cents a year. If it's $2.50 now, what will the price of gas be in 5 years? Again, it's a constant rate of change, 5 cents per year, over and over again. So we know we should be looking at something that's linear. The M value now, because it's falling by 5 cents a year, should be a negative 0.05. Our B value is still the same. It's still $2.50 at the start. We want to know what's the price of gas in 5 years. We should expect it, because it's falling, to be less than $2.50. Our linear equation is going to be y equals negative 0.05x plus 250. We plug in our time. X is going to be 5. And so after 5 years, we should see negative 0.5 times 5 plus 250. I multiply these together. I get negative 0.25 plus 250, which is equal to $2.25. So after 5 years, we should expect the gas to fall to $2.25. Lastly, example 4 says the price of gas has been falling by 5% per year. Again, a percent change tells us we're looking at exponential. Because it's falling, our R value will be negative 5%, which is negative 0.05. The starting value Q naught is still $2.50. And so our equation is going to be Q is equal to 2.50 times 1 plus a negative 0.05, or 1 minus 0.05, raised to power T. We clean that up, We get a nice model that says 2.50 times 0.95 raised to power t. So this is our model. Again, we want to know what's going to happen in 5 years. So I'm going to let t equal 5. I'll plug it in and I'll find the new value of gas. 2.50 times 0.95 raised to the 5th power. We go to our calculator. We want to raise that to the 5th power. And when we round to the nearest cent, we get $1.93. So we can expect the gas price to fall to $1.93 in this model. So these are our examples of linear and exponential growth. Remember, the key things that you want to do is identify how are things growing or decaying. Are you growing by a percentage? Are you growing by a constant amount? That will allow you to differentiate between linear and exponential. Each model, whether it's linear or exponential, has two important pieces of information for you to grab. The rate of change, which in the exponential model is r. In the linear equation, the rate of change is m. And then the other important piece of information to grab is that starting value. In the exponential model, it's played by Q naught. In the linear model, it's played by B. Once you have those two pieces, it's just a matter of plugging it in and evaluating. For money, we always round to 2 decimal places. That's it for section 8A. Hope you have a wonderful day.